Hello, I'm Greg Allison with Galactic Greg's, coming to you from the F1 engine at the very front of the Marshall Space Flight Center. This rocket engine, the F1, is the mightiest, most powerful, liquid-fueled, single-nozzle engine ever developed by mankind. And today, 50 years ago, July the 15th is today, 50 years ago, it was sitting on the pad at the Kennedy Space Flight Center. 5 of these, not this one specifically, but 5 of these engines were on the first stage, the S1C stage of the Saturn V launch vehicle. And they were prepared the next day, the 16th of July, to launch the Saturn V on the Apollo 11 mission to the moon, carrying Aldrin, carrying Armstrong and Collins to the moon for our first ever lunar mission, landing mission. So this engine produced 1.5 million pounds of thrust per engine. 5 of them together, and this is a huge engine, this produced 7.5 million pounds of thrust. That was just enough to get the Saturn V off the pad, and slowly accelerating up, at least initially. And then it, of course, accelerated quite nicely. Now I want to give a quick disclaimer. I am a contractor here at Marshall Space Flight Center, not an employee of NASA. And I also do not speak for the company I contract to, nor for NASA. I speak solely for Greg Allison with Galactic Greg's channel here. All that said now, so let's talk a little bit about this engine. As I said, 5 of them on the S1C stage, and at 1.5 million pounds of thrust each. It might be noted that was the thrust level from all Apollos up through Apollo 8. Actually, Apollo 9, the one we launched on now, Apollo 11 and forward, this engine actually produced 1,522,000 pounds of thrust. It went from burning from 150 seconds to 165 seconds. That enabled this rocket and other performance gains on the Saturn V vehicle, enabled them eventually to take the lunar rover to the moon. Extra payload. And the lunar rover was also developed here at the Marshall Space Flight Center. Now, before I go further into performance of this engine, one other thing I'd like to add is a promotional for the Huntsville Alabama L5 Society. We have a panel on the lunar landing. Actually, this panel is on the date of the splashdown because we're looking forward to the future. We're going to have Apollo veterans, Apollo engineering veterans, people to develop this stuff, and new engineers, young guys who are developing our landers to get us back on the moon, talking to us on this panel. And the panel is going to be the past informing the future, because HAL5, the Huntsville Alabama L5 Society, is a forward, future-looking organization. So we want to remember the past, but keep our eyeball on the future. The program is free and open to the public. It'll be a great program. Link below, hal5.org. Please consider attending this public. We'll be at Straight Ale Brewery. And of course, you can buy dinner. If you choose something to drink there, that's up to you. Now, back to this engine. As you can see, all these tubes in here, these are the coolant tubes. It was the fuel that was used, the RP1 fuel, to cool this engine, because this engine got mighty hot with all that combustion going on. And it's a gas generator cycle engine. So it's got a huge turbine up here, a single turbine fed both the oxidizer and fuel pumps. And that turbine is a gas generator. It had a pre-burner. The pre-burner turned the turbine, and then that turned the pumps. You see one of the pump heads up here on one side, and there's one on the other side. And this thing actually, the turbine itself rotated at 5,500 RPM. Pump over here, turbine in the middle, gas generator system. And that's 41 megawatts. I think I mentioned, maybe did I mention it produced 55,000 horsepower. Amazing, right? And it consumed 24,811 gallons of RP1 per minute. RP1 was the rocket grade kerosene fuel used on this rocket engine. And combined, all 5 Saturn V's engines, F1 engines used on the Saturn V, consumed 3,357 gallons of fuel per second. I think that counts the oxidizer, which was flowing at a rate of 5,683 pounds per second. You know, the pounds and the volume don't equate exactly, but they do translate. So the cool thing about this engine is that a lot of people think that NASA lost the blueprints and can't build anymore because of that. No, that's not the case. NASA has all the blueprints and the plans, the drawings for everything used on the Saturn V rocket. The problem is that you can't do things the same way we used to. Industrial processes have changed a lot, and a lot of knowledge was not captured on those shop drawings. Look, we have a bird nest in this rocket motor. How about that? Birds are everywhere, including rocket engines these days. Okay, I suppose there's a bird nest up there. The Saturn V F1 engine, I'm getting off of the bird there. It is reproducible, and we've looked at reproducing it, but we can't use the techniques because the shop drawings did not contain information used on how to actually build each and every part, like how much cutting oil to use in a specific application. The knowledge that the guys had on the shop floor did not make it into the drawings, and a lot of knowledge was also rendered on napkins and other things. However, it was proposed to build a variant of this engine, F1A, which would have been a follow-on for subsequent Apollo missions, at which we thought we were going to fly, that would have produced 1.8 million pounds of thrust. And that was at the time using the techniques of this engine. Since then, an engine design has been reconsidered for what we call an F1B. The F1B is intended to use the same thrust level, 1.8 million pounds of thrust, and it was designed to be used as a liquid strap-on for the SLS as a follow-on to the solids that are on it now. So the F1B would not have used as many parts and used modern manufacturing techniques, probably been a lot cheaper and a lot more reliable even than this engine. This engine did have development problems, issues in the early days of instabilities at 1.4 kilohertz and 24 kilohertz, and what they found early on is they had to have coaxial injectors and some baffling to solve those problems. It caused some catastrophic failures in the early test days of the engine. But they worked it out. They used bombs basically detonated underneath the chamber engine here, or underneath the nozzle, to characterize the flows and the stability problems and figure that out. And then they got that worked out so well that if they introduced an artificial instability, it would self-dampen in less than 1/10 of a second. So this was a workhorse, very reliable engine. And could be a very reliable engine in the F1B for some future application, should someone so choose. The Russians had the RD-170, which produced more thrust, but it was a 4-nozzle engine. They used it on their Inertia launch vehicle, which they launched their Buran space shuttle on one time. Maybe they launched Inertia on some other occasion before that. Before they launched the Buran, I'd have to look into that. But in any case, as you can see here, one of the things that you can't replicate today is necessarily all the valves. Valves change in design, the vendors change. You don't always get the same models, even from the same vendors. And there's a lot of valves in here, valve drivers, solenoids and systems to drive all these things, electronics to drive all that. It's quite complex, and this is just on the engine. The stage itself would have had a whole lot more of that than this had. The reason a lot of these pipes are bent the way they are and have the flex tube is to accommodate the heating and contracting, which is very significant, of the metals used to feed these things. So you've got to have some way to flex that, or the plumbing will break and shear on these things. I was taught that lesson by Conrad Dannenberg, one of the original V2 rocket team members. And if you ever look at a V2 engine, see how the pipes are bent, that's before they had all the flex that they got in here today. That's why they bent them that way, because originally the pipes just ripped out due to the thermal stress that all this stuff had to have. I mean, basically this thing had to be able to go to minus 300 C for the cryogenic fuels, and I think you had to go like 1500 degrees Fahrenheit for the various hot side of the process. So this engine was also figured to be used on something called F1 flyback. You might recall the earlier days of the space shuttle, they had a manned flyback booster concept. It was too expensive, they scuttled it, but then they competed a first stage S1C variant with wings, remote piloted, to come back against the solid rocket boosters. Now that proposal was for about $200 million more development money than the solids. It was supposed to save money over the long term because it was supposed to be reusable, at least to a large degree, bringing the fuel tank back. Now, I don't know what degree, if they had some plans to be able to reuse this thing, because this was before we really were going for reusable engines, although some power head and some components could have been refurbished. This is the SSME, which is the now the RS-25, which is to be used on the Space Launch System. Was used on the Space Shuttle. It's a reusable engine, refurbishable, that is. That's the J2 engine over there, which was the upper stage restartable cryogenic engine for the second and third stages of the Saturn V. 5 on the second stage, 1 on the third stage. Now, all that said, this F1 flyback concept was only $200 million more in development cost, but they decided to save the development cost, which is typically what's done. But in the end, as we know, the Challenger that was destroyed and lost 7 precious lives and had to replace Challenger, a $2 billion space shuttle. So don't know about the gains from the cost side, definitely not on the astronaut life side. But we learned a lot of lessons from that, and we have very good, reliable booster segments today with a very safe joint system compared to what we had in the Challenger days. Sometimes lessons are learned hard. But in any event, this is the F1, the mightiest single nozzle rocket engine ever devised by man. First tested in 1950s, designed by the Air Force. It was intended, Von Braun sold it to the Army Ballistic Missile Agency as a troop transport rocket, although political channels don't use it to go to the moon with this thing. But at least that's how they sold it through the system to Congress. And it did take us to the moon. And who knows, maybe one day this rocket motor may rise again and take us to other points in space. We shall see. Whether it does or not, it fits and served history. So my hat's off, my salute to the F1 rocket engine. Please check my link below, support my channel. If you haven't already subscribed, click the update notification bell. I'm going to do a lot more videos on rocketry, rocket engines, probably and going in great depth in some of them. I will start out initially with some really basic, simple stuff so the layperson can follow along in the future as I develop the rocketry talks. And so please click subscribe and bang the update notification bell. That's how you get the notifications of all the videos I'll be putting out in the future on this and many other space and science related topics. Thank you for watching.